So let me erase this stuff right here. And I'm going to, on notes, I just printed out section 5.8 on the notes about law of conservation of matter. And let me see. So I don't know how well if you guys can see this, but I'm gonna make a video. I'm doing a video right now of this. All right. So for your test, what you need to do is be aware of all the equations, mainly like for work. Go over on the like the practice quizzes that we gave. Just make sure you know, for example, work is a force parallel direction of motion times distance. Know that force is mass times acceleration. The net work done on an object is equal to the force of all the work done by all the forces applied to that object. Work. You know, like for example, a lot of times we'll say friction. We'll say something's going along with friction, and I'll say, okay, the work done by friction and the work done by, I don't know, we'll say R. So like, say that Mr. R is pushing this box or something like that. Okay, well, I'll give him a little hat there. Okay, he's pushing the box. So you have the force R here, and then you have friction going the other way. Force of friction going this way. All right. So the work plus work by force R, work by friction, make a positive or negative, is your net work. Net work is also the force times the distance. I could probably write it a little bit lower if possible. I don't know how great this will be. You guys will be able to see me on this other video too. What's another equation? All right. Now, there is something else, and that is when you have an inclined plane. So make sure you remember these sort of problems. Like you're pushing a block across the ground, and you say, okay, what is the friction? Oh yeah, I didn't tell you the friction equations. There's a lot of equations here. Friction is mu k times the normal force. So you might go back and watch some of the videos in this chapter if you're not sure, if you don't quite remember this. But how do you find the friction force? All right. So what I could do is just say, let me draw this a little higher and bigger so you guys can see it. So like if I want to find the friction on this box, I got to know its mass, and I have to find its weight. So remember, the weight is mg, 9.81 times the mass. So like to say it weighs 5 kilograms. Well, 5 kilograms times 9.81 will give you the FW, or I'll say FWT, the weight. Now, that would be pulling downward, and then normal force would be the force that is balancing it out. Okay, you remember this came from the last chapter, but you find the friction force by a constant I'll give you times the normal force. So if I had 5 times, it's about 9 or about 10, about 50 newtons. It's about 50 newtons is the weight. So here 50 newtons would also be the normal force. All right. So really, if you know how to calculate friction force, and then if you know the force, if I already tell you the other force this guy is pushing is like, 200 newtons or something like that, then you'd be able to figure out the work he does would be his force times the distance it went. I have to tell you how far it went. So I'm just kind of like giving you a quick overview. What are the equations you need? You need FMA. You need force is work is force parallel times distance. You need the net force is the sum of all the works that were done, the work by every single force. You need to know how to find the normal force from the weight. And I wouldn't worry too much about the problems with the there will be something with an inclined plane, and maybe there'll be something where, remember we talked about where you pull the box at an angle. And let me say something about that real quick too. Like if I pulled this up at an angle, then I'm going to have to find out, like if that's force Y for yellow, okay? I'd have to find out what is the X component, Fx, and what is the Y, Fy. Okay, now, Fx is the only part of that force that will do work. So if Fy were pulling this box, and I want to find the work done, I'm going to have to calculate Fx. If Fx times the distance it went. So that will become Fx. When you're pulling it at an angle like that, that becomes Fx times the distance. Okay, I don't want to make that always the case, but it just depends on the picture. Okay, and of course to do that, I'll always give you the angle, and so sine will tell you Fy over. Well, I couldn't call it Fy, can I? Oh no. Well, F, I'll call that force yellow F. Fy over the hypotenuse will give you sine. Fx over the hypotenuse will give you the cosine. Cosine will be Fx over that. So you can solve those two. And then don't forget the inclined plane. I need to give you, I'm trying to think, I might have a practice some problems if you want to do them. But you can just look over your old worksheets. I might have a little practice take-home thing for a test. Maybe I should just give you that. But when you have the inclined plane, just remember if an object is on this incline, then just say if it's 30 degrees, I'll put 30 right there. Okay, 30. So you draw a force straight down, and then you get to draw the triangle within it. And I'm trying to record this, and we'll see if it works out. Okay, so you draw a triangle within it. One is parallel to the surface, and one is perpendicular. Okay, that's Fy, and that's Fx. And so in this one, if that's 30, then your top angle is also 30. And remember, sine will be Fy over the hypotenuse F, the weight. That's your weight coming down, mg. So Fy and Fx. That should get x. Okay. So only if I needed to lift this up, I have to overcome gravity. And Fx, you might remember, is really, really small compared to the weight. It's easier to push something up the ramp. If I'm equaling Fx, that will be the minimum force needed to keep it in place or to move it up. It's kind of a strange thing, but that's the way it works. There could be one thing. I can imagine I'll say find Fx, find Fy. I mean, this one might have one little small thing on it, okay? But now the problem where you're pulling a box along, that one is a lot more likely to be like on a major calculation problem. I don't know if this is really strange for y'all to see it this way. Well, I was hoping to show you one new thing. I don't want to go too far. But what I'll do is, I'm going to show you something right now. And this will be a bonus, okay? So if you can do this on the quiz, then I'm going to post a video of it. The video, it looks really strange over here too. Y'all to see how this is. I'll be looking the other way, talking in the video. But I'm going to try and show you one little thing on 5.8. It says law of conservation of energy. Now, this is a kind of a neat thing. And here's how I did it on the worksheet. I'm going to kind of change it the way it was on the worksheet. It's like a roller coaster, okay? So like you have a roller coaster going like that. And let's just say this is A, this is B, and this is C. And let's just say that this height for A, I'll say is, I don't know, the height of A is, we'll put 20 meters, okay? Then if the height for B, that looks like half, so we'll say it's 10 meters. Now, there's a couple of things that are kind of neat about this, and I just wanted to show you. There's one equation that talks about kinetic energy. It's 1/2 mv squared. By the way, you do need to know about that. That's another equation you should know. And you should know that the work done on an object is the change in kinetic energy. So it's kinetic energy final minus initial. Well, here is something also interesting. This would be a bonus. There's another equation called potential energy. And there's one thing called gravitational potential energy. And the way it works is mass times gravity times the height tells you the potential energy. Potential energy means, you probably heard of that before. It's like, well, like it says the word potential. Like if I take this calculator, right now I'm holding it up here. it has energy relative to my hand below it, okay? But you don't see it moving. It has potential energy. Because of gravity, it has potential. If I let go of it, look at what it does. It changes from potential, it changes to kinetic. Oh, to kinetic. Okay, that's good. To kinetic. All right, so now here's what the math is going to show. Right now, if it's this high, let's just say it has 10 joules of potential energy, 10 joules. When it hits my hand, it hit my hand with 10 joules of kinetic energy. Here, it's got 10 joules of potential, 0 kinetic, not moving. 10 potential, 0 kinetic. All right, now when I let go of it, when it hits my hand, well, and it fell, but when it hit my hand, all of the potential energy was gone, we'll say. So it had 0 potential and 10 kinetic. So it went from 10 to 0 in potential, and then kinetic from 0 to 10. All right, I'll try and show you this on an equation. So because of this, here's the neat thing. We could figure out, well, there's a couple of things we can figure out. We could figure out what the height of down here at C is. We can figure out how fast it will be going when it gets to the top of B. So what will it be going? Like let's just say that right here at A, you start a roller coaster. You start something rolling down. It starts rolling down from A, then over B, then over C. Say that at A, at the very top, it's going, we'll make a number, 50 meter. That's pretty high, actually. I'm going to make it 20. 20 meter per second. 20 meter per second is about like, you can almost double it, like 40 miles per hour, or maybe even more than that. You get about 40, 45 miles per hour. So it's this going, well, it doesn't matter. Oh, no, 30, make it 30. I want to change it because I have a 20 there. It could get confusing. So let's just say a car is going 30 meters per second right here at the top of this. Now, when it goes down, it's going to keep going back up. What will its speed be, velocity, when it gets to the top of B at 10 meters? What will it be? This might also be an easy one to kind of figure out from looking at it, but oh well. Let me just try and show you. Here's how the problem works. The law of conservation of energy says energy cannot be created or destroyed, but it can change from one form to another. So what it says is, I can start out with a certain amount of kinetic energy at A, at point A, and a certain amount of potential energy at point A. So kinetic energy A, potential energy A, is equal to, it will be the kinetic energy at point B plus the potential energy at point B. Now, again, this will be a bonus, but this is a very important concept. And it looks a lot like the one we did before with the work, how work is to change in energy. So here's what I'm going to do. I'm just going to go through the whole thing. 1/2 mv, I'll put it A squared. Okay, sorry. So 1/2 mva, that means what was the velocity when it's at A? We said 30. 1/2 mva squared plus mgh, and we'll say the height of A, is equal to 1/2 mvb squared plus mgh, the height of B. And this really does work out. It's pretty neat. This is a whole lot easier. I remember I told you like last week to say, instead of doing the long kinematics equations from last semester, or final velocity minus initial velocity squared plus 2a delta x, this allows you to omit a lot of that stuff. In fact, you'll see that a lot of it is related, the whole squared and squared thing. Okay, well anyway, here we go. So I'm going to try this. We're going to try to find out what is the velocity when it gets to, what's the final velocity. So you could also call this initial and final, and that's true. This will be your initial, and we'll say B. So on the worksheet, I'll probably just ask you to do a couple those A, B, and C on the worksheet, the first problems, and say, like, you can compare any 2 points you want, A to B, B to C. You could even find the height of C, for example. So you could find anything in here, but I'll plug in what we have. Now, here's a very amazing thing you like about this equation. And this is really a neat and bizarre thing, thanks to Galileo. Notice M, 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 and M. The mass does not even matter. And I didn't even give you the mass on the problem. And sometimes I'll give this on a quiz or a test in past years, and they're like, you forgot to give us the mass. And I don't want to just tell them that. I'll say, well, look carefully at the equations. There's something there. So you can ignore the masses. They can all cancel out. That's good. Sometimes the 1/2 can cancel, but not in this case. So 1/2 times the initial velocity was 30 squared, 30 meters per second, plus gravity is 9.81, and the height here was 20 meters. All right, so 1 times 30 squared plus 9.81 times 20 equals 1/2 times whatever my final velocity squared is. Now, what makes it a little tougher is because it has to be squared. At the end, we got to get the square root, okay? Plus 9.81 is the gravity, and the height is 10 meters. All right, so I'm going to have to do the math. Actually, I better just, I don't know, on this video you won't be able to see me. On this one you could. So 30 squared, what is that, 900? So 30, I just made this problem up on the spot here because I thought it's easier to do like a worksheet. So it's 900, and half of that will be 450. So 450 plus 1962, I won't worry about the sig figs here, equals 1/2 v squared, oh boy, I'm going to really run out of space, plus 98.1. Okay, let me see if that, yeah, that actually, it actually is fitting here on the thing up here. You might not see it so good now. 450 plus 1962, 1/2 v squared plus 98.1. Let me do all the math. 450 plus 1962 minus 98.1. Okay, then I got to do times 2 to get my v squared. So the next step, if you wanted to write one more math step, 4628 equals v squared. Then, of course, you got to get the square root of that. And it's 68. Okay, yeah. 68 meter per second is the velocity it's going to have there. So, see, here's the thing. I didn't really mention this so much. Wow. I should have let the velocity be 0 at the top of the hill. Because if I had done that, it would have been easier. You have 0 terms. So if you ever have a 0 velocity, that's actually better. But what happens is we're going over a roller coaster. Normally at the top of the roller coaster, you just barely have, you're like 0, then you fall down. It was already going like 70 miles per hour right here. And now the hill's going to make it go faster. This is going to be a mega roller coaster. So you're really going fast here. And so by the time you get up there, you're going 68. That's incredible. So anyway, I just wanted to show you that one little bit. I know it's crazy to throw